Hello, my name is Damien Imbs, and I'll present you a joint work with Emmanuel Godard, Michel Raynal, and Gadi Taubenfeld. In this work, our goal is to obtain tight space bounds for leader election using an anonymous memory. We also consider two generalizations of leader election, namely de-election and exact de-election, which I'll define in a moment. In the leader election problem, every process must output the same identity, the identity of the leader. In the classical, that is, non-anonymous shared memory setting, Steyer and Peterson obtained the following results. If not all the processes have to participate, that is, some may participate and others not, then the ceiling of log n plus 1 registers are both needed and sufficient. So it's a tight bound. When every process has to participate in the election, they give an algorithm that solves the problem using 3 registers. They also state a conjecture that says that 3 registers are needed. In this work, we actually disprove this conjecture, and we do so by solving the problem using a single register. Now, in this algorithm, the register, the only register, has several fields. The first field is the ID field, which contains the identity of a current candidate or bottom. Initially, it is equal to bottom. The second field is called discarded and contains a set of identity of processes. These processes have already lost the election, and they know it. Obviously, initially, this set is empty. The third and last field is called phase. Now, the algorithm can be in 2 phases, either electing or committing, and it starts in the electing phase. In the electing phase, all the processes start as being candidates, and the phase ends with a single one remaining as a candidate, the leader. In order for all the processes to know who the leader is, we need a second phase, the committing phase, that starts with a single candidate and ends with every process knowing the identity of the leader. The general idea is the following. Every process starts as a candidate. When a candidate observes a write by another candidate, it considers that it lost the election, and it then writes to the register and includes itself in the discarded set, and it writes bottom in the ID field. Second possibility. The candidate observes a write by a loser. In this case, it writes to indicate that it observed the loser by including the identity of the loser in the set discarded, and it writes its own identity in the field ID. Now, once a candidate sees n-1 other processes in the set discarded, it knows that it is the only candidate remaining in the system, and so it has been elected leader. Now, the second phase, the committing phase, is similar. The difference is that the leader is the only candidate. And as I mentioned earlier, this phase happens in order for every process to know the identity of the leader. I mentioned 2 generalizations of leader election. In the de-election problem, at most D-leaders can be elected. In the exact de-election problem, exactly D-leaders must be elected. Now, in the non-anonymous classical shared memory setting, these 2 problems can be easily solved using iterations of leader election. So you just have to run D different leader election and you solve both problems. In the anonymous setting, things are a bit trickier. So, for some values of m, the size of the memory, and of n, the number of processes, the problem may be possible to solve for some values of d and impossible for others. For example, for some values of m and n, 2 elections may be impossible to solve, while 5 elections could be solved. So in this setting, d election and exact d election make sense as separate problems. Our main result is the following. In a system consisting of n symmetric processes communicating through m anonymous registers, we have the following. Leader election can be solved if and only if the greatest common divisor of m and n is equal to 1. D election can be solved if and only if the greatest common divisor of m and n is less than d. And finally, exact D election can be solved if and only if the greatest common divisor of m and n divides d. Now, in order to prove these results, we give an algorithm that solves exact D election and an impossibility proof. Now, what is an anonymous memory? In a classical, non-anonymous shared memory model, processors agree on the indexes of shared registers. So, if process I accesses its 8th register and process J accesses its 8th register, they will access the same register. In an anonymous memory, things are different. Each process has its own map to access the registers. So, if process I accesses what, from its point of view, is the 8th register, it will not necessarily access the same register as Pj if process J accesses what is, from its point of view, the 8th register. In the example we have here, if process I accesses the 8th register and process J accesses the 3rd register, they will access the same one. So each process has its own map to access registers. Now, the concept of memory anonymity has been used implicitly in the early 80s in a paper by Rabin, but it has only been formalized and conceptualized recently by Gadi Taubenfeld in his paper from PODC 17. Another way to view memory anonymity is to view it as an adversary. So the adversary shuffles the memory map for each process. The indexing of the memory is a permutation at each process. So this prohibits the processes from agreeing on the indexes of registers. Now note that this is not necessarily true for all combinations of numbers of registers and processes. So in our paper from Sirocco from last year, we give an algorithm that de-anonymizes a memory for certain combinations of memory size and number of processes. Concerning process identities, various models are used in the literature. The first one, possibly the most common, is to have unique identities from 1 to n. Another quite common one is the one used for comparison-based algorithms. In this model, processors still have unique identities, but these identities come from a namespace of size much greater than the number of processes. In this case, if you have a number, you cannot know if it is the identity of a process or not. But what you can do is know if an identity is greater than another one or not. Another common model is process anonymity. In this model, processes do not have any identity, and there is no way to identify individual processes. The model that we use in this work is process symmetry. In this identity model, processes have unique identities, but these can only be compared by equality. So there's no a priori agreement among the processes on a total order on identities. The only test that is allowed is equality. So if you have two identities, you cannot say that one is greater than the other. You can just say, are they the same or not? We also have a classical requirement, that is that processes have the same code. Otherwise, the identity could easily be embedded in the code, or the code could be used to break the symmetry. So we prohibit that. So to sum up, our model is the following. We have M anonymous registers, so there is no a priori agreement on the indexes of the registers. We have N anonymous symmetric processes, so IDs cannot be compared except for equality. And a process knows N, the number of processes in the system, and M, the memory size. It knows its own identity. It knows that all identities are different, but initially it does not know the identity of the other processes in the system. In order to solve election in this model, we will use a famous result from the 18th century, that is, Bezout's identity. Bezout's identity states that if we have m and n two positive integers, then there exists two other integers u and v such that u times m plus v times n is equal to the greatest common divisor of m and n. We can then easily obtain two positive integers u prime and v prime such that u prime times m equal v primes times n plus the greatest common divisor of m and n. Now let d be equal to L times the greatest common divisor of m and n, with L a positive integer. We then have that L times u prime times m is equal to L times v prime times d n plus d. This is the form that we actually use for the algorithm. We use Bezout's identities to solve exact D election in the following way. With m registers, n processes, and d that divides the greatest common divisor of m and n, which is our necessary and sufficient condition to solve the problem, we have u and v such that u times m is equal to v times n plus d. The general idea of the algorithm is the following. Each register implements u single register leader elections using the algorithm I presented earlier. Every process competes until it has won v of these selections. And once every process has won v elections, there remain u times m minus v times n, that is, d elections, and these are used to elect the d leaders. Now there are a few subtleties. A single register leader election, as implemented by our algorithm, can progress only if all processes participate. And the process cannot win if it has already won v other competitions. So once it has won v competitions, it must not be candidate in the following ones until every process has won v competitions. That is why we could not use our single register election algorithm as a black box, and we had to adapt it in order to obtain the exact D election algorithm. So the exact D election algorithm uses the mechanism of the single register leader election algorithm, but it does not use it as a black box. Here is a sketch of the proof of our impossibility result that shows that our bounds are tight. Suppose that the greatest common divisor of m and n is greater than d. Then partition the processes into GCD of mn groups. Run the processes in lockstep and arrange the M registers on a ring. Here is a sketch of the proof of our impossibility result that shows that the bounds are tight. Suppose that the greatest common divisor of M and N is greater than D. Then partition the processes into greatest common divisor of M and N groups. Run the processes in lockstep. The mappings of the processes will be defined as follows. You arrange the registers on a ring, and for processes in the kth group, the register X corresponds to the register K times M over greatest common divisor of M and N plus X mod M, as seen by an external observer. So the idea is that the mapping starts M over GCD of Mn apart, and they follow the same cyclic order. Each group of processes will then always stay in the same state, and processes then cannot break symmetry among groups, and thus the problem is impossible to solve. As a conclusion, we have presented a single register leader algorithm election. And this algorithm disproves a conjecture from a paper that appeared in PODC more than 30 years ago. We used the anonymous memory model. This model is a quite recent communication model. If you want to know more about it, it has been introduced by Gadi Taubenfeld in his PODC 17 paper. In this model, we give a tight characterization of the solvability of leader election, D-election, and exact D-election. The condition in order to be able to solve the problem is quite interesting. It is based on the greatest common divisor of M and N, and it is not threshold based. Now, these results relate to a previous result that we had, which was tight bounds for the mutual exclusion problem in the same anonymous memory model that we had in a paper in PODC last year. And I mentioned earlier that for some values of M and N, the memory can be de-anonymized and then used as a classical non-anonymous memory. In a Sirocco paper from last year, we give an algorithm to obtain such a de-anonymization of the memory. And we also give algorithms that are simpler than the one presented here for some very special cases of leader election. Thanks for your attention.